So thank you everyone for coming. This is talk, but first a bit of an introduction. My name is Raúl Chouza, and I first like to do a little bit of a preamble. One of the hobbies I really enjoy is collecting and playing board games. I can be very enthusiastic about deconstructing them and figure them out. Figured out like how the different game systems intertwine, or how a given topic influences gameplay, or it's always fun just to read the designer notes of a game. I can also be a bit of a pessimist when it comes to actually play them. I just don't always have the time, space, and energy required, less so the availability of other busy people. A more asynchronous style of play will sit very well with me. Some game adaptations do this via a play-by-email model, where you submit your turn to a server somewhere and wait for the next player to do the same. It takes more time, but I like this because I don't have to rush through the game in a single evening. Maybe it now takes weeks or months to complete, but also it has the nice side effect of making sessions very memorable as you carry them through your day. I have always wanted to game a more sessional game I enjoy like this. So I decided to start with the game For the Crown, which you can see here on the screen. It's a game by Jeremy Leonard, and this game combines chess with deck building elements. So that means it is a chess variant where you play cards to break the rules in interesting ways, for example, having multiple kings on the board, moving multiple pawns in a single turn, or even invoking the undead. I do realize that distilling all these rules into code is very ambitious, as I have no clue how to encode them. And because I have no definite model in mind, I wanted a tool that will help me to keep whatever abstraction I came up in check. Also, I really wanted to try Gleam for real. Gleam is a programming language that compiles down to Erlang. In many senses, I will go as far as to say that Gleam is Erlang with a couple of quirks. Let's look at some examples. Here, we have Gleam and Erlang side by side. On the left, there's a Gleam coordinate module, and on the right, the generated Erlang module. If we look at the top of our Gleam file, we can notice that there's a coordinate type that wraps two numbers, one for the x-axis and one for the y-axis. And below, we can find a function that does the arithmetic on the coordinate type, in this case, for addition. At the right, we have the code that the Gleam compiler generates. And while not exactly the same, we can appreciate how both blocks share a very similar structure. Erlang code generated this way can be loaded to the Erlang shell or to IEX. It can be tweaked into your Rebar or Mix project. And really, loaded into an implementation of the Vim, as long as it accepts Erlang files as its input. On the syntax department, Gleam tries to keep things simple by mostly having only one way of doing things. Maybe the most outstanding example is how all branching logic is managed by a single case statement and pattern matching. Gleam likes to keep syntax sugar to a minimum, and most of the expressiveness will come out from composing your data and functions together. Most importantly, Gleam retains the semantics of Erlang, and any kind of procedural programming you can do in Erlang, you can do in Gleam. I say procedural programming and no concurrent programming because Gleam, the language, is separate from OTP. This is because Gleam tries to be platform agnostic. It knows how to compile down to Erlang, but it doesn't know too much about the Beam virtual machine. For that, there are separate OTP libraries that do the bindings to Erlang functions. Here we can see two examples of binding functions. One uses the Erlang standard library for getting the local time, and the other one uses the Elixir standard library for getting the daytime, in this case, the UTC now. As a side note, Gleam also supports another compiler target, which is JavaScript. And similarly, JavaScript generated this way might as well run in a browser, it might run on Node, it might run on Dino, and as long as you have the bindings and the runtimes in your machine, you should be fine. However, I think it is safe to say that Gleam retains Erlang semantics because the beam is its primary target. And probably the most prominent quirk is that Gleam features types with really nice compiler errors. It also helps that the compiler is fast, giving quick feedback when needed. I mentioned that translating this game was ambitious, so I decided to reduce my scope and go for a basic implementation of chess. This is what I did for this presentation. So right here, we can see the board, we can see the chess pieces, and we can see how when we hover over the chess piece, we can project the path a piece can take. And after a couple of moves, we will be able to see how different pieces can collide and capture each other. So for example, when a piece can capture each other, there's a little red flag marking what piece can we capture. I would like to show how this was built and constructed. There. So welcome to my talk, Crossing Boundaries with Gleam, where we are going to explore an implementation of chess and see what parts of the design fit as a purely functional construct and what parts as a runtime component of our system. Let's review the model for the different entities in the game. For the most part, what I refer as an entity is just equivalent to a Gleam type. Usually, Gleam types can be created by using literal syntax, and the fields can be accessed by using pattern matching or a dot syntax. However, when you define a type with the opaque keyword, as we are doing here in Turn, your type is now restricted. Other modules cannot create or pattern match on that type. Only the module that defines it can do so. And the only way to create and retrieve information is now through the module's functions, which becomes the module's API. A similar concept to what we find in Phoenix context, where your context becomes the API to consume your data. But this one is enforced by the compiler. This is more or less how the current implementation is layered. We have different game entities along with their relationships. First, there's the game state at the top, which holds round information, the player's information, and a coordinate grid with the pieces. By itself, it's just a wrapper type and not much more. We have player-related entities. A player by itself just contains an identifier, which could be a new ID or a name or anything you can hold up to. Then, the player type holds a number set of the players along with the turn sequence. Then the grid is a map with coordinates as keys and positions as values. Each check square or position holds relevant information, like the piece that occupies it, the player related to that piece, and the paths the piece might navigate at that point. Then we have a piece type, which is self-referential and takes advantage of sum types. This means that there are different shapes for the same type, which is piece. The grid is where most of the fun of the app happens, because ultimately, we must calculate how a piece moves through the board, which requires us to model movement patterns, blocks, and possible captures of rival pieces. To achieve this, I have a pair of entities, path and rule, which are used in a rules engine that can evaluate the directions a piece might take. A rule type is used to compose movement constraints. Then we use those constraints along a direction to trace the path of a piece. We can appreciate the end result with a unit test, where we are setting up the board with a knight at position d4, retrieving the position d4, and then asserting that this piece has 8 valid positions to move in the board. In the end, the path entity lets us retrieve a simple list of coordinates. Finally, let's have a look at the round context, which is currently rarely used. On one end, it contains a turn type, which is just a simple counter that is incremented by 1 each turn. On the other, we have a phase type. And as far as I know, chess doesn't contain phases per turn, but this game does. And while not used in the earlier demo, I think the next example is really neat to look at. In this variant of chess, each player has different stages per turn that they go through. The first one is to move a piece or deploy a new piece to the board. The second one is to play a card to break a rule of chess. And finally, we can buy new cards that fit our strategy. And we repeat again and again until the game is ended. Transitions of this state machine can happen through functions. We can define a start function to set the initial state to move. Then the next function will rotate through the phases. This simple state machine is trivial to do in any language. But because our transitions are represented by types, the added checks at compile time can be beneficial in more complex scenarios. All in all, this is the general structure of our chess game. I had to think thoroughly about this design, but it's very far from perfect. There were a lot of misses which led me to constantly reshape the inner details. For example, the current board has many layers of abstraction, and at these points, it feels a little bit overdone for what at core is just a map. The current rule system can be hard to disentangle, and mainly because I'm passing the whole state of the game around. And to get valid movement positions for a piece, I do 3 layers of transformations on the results. Granted, these issues have very little to do with Gleam and more to do with my design. Programming in Gleam gave me a very strong sense of how my code base is structured, which I'm attributing to thinking so much in terms of custom types. And for the smaller details that I don't keep in my head, Gleam quickly identified errors with useful hints. This meant I could make drastic code changes and trust that in the end, the compiler will guide me to non-breaking code. Emphasis on non-breaking, not necessarily correct. With all these elements, I built a complete functional implementation of chess. Once Gleam code is compiled through Erlang, I could load it on an IEX session and execute the commands on the left, which are creating a new game, setting up the players, deploying the pieces, and moving pieces on the board. However, this functional version is not very playable. Running the commands on the left will give me the very large data structure on the right. Obviously, we want to represent the game state in a more board game-like fashion, as I showed in the video. We got many options here. We could just draw in the terminal with Unicode chess characters, but I wanted something more graphical. We could do a web page that uses HTML or Canvas, but I didn't want to deal with setting up a web page right now, at least not for this talk. We could have tried WX widgets within Gleam, but the API is extensive and requires a lot of learning. For this talk, I just wanted to display something. So balancing the pros and cons, I decided to try out Elixir's Scenic library, which from the get-go is familiar because it's Elixir. And also, its API draws some parallels with LiveView, which I have used in the past. Scenic works under the concept of a scene and a graph. A scene is a process that stores the state and triggers draw commands to the screen. And a graph is a struct that tells the machine where and what to draw. To render a chessboard, I'm using 2 scenes. My home scene hosts the whole game state information and updates the state of a board component. And the board component is only capable of drawing any state that is given to it, but it cannot really update the game state or positions by itself. It's pretty functional in that sense. But it does one thing. It sends back input events to the parent so the parent can get feedback on the current mouse position. Now that we are hosting the game state on a process, our chess game stopped to be purely functional. We are now entirely dependent on the rendering behavior of the scene process. We are in a runtime now. To make this possible, I had to wrap Gleam chess into I had to wrap the Gleam implementation of chess into a mixed project and expose it as a library to an Elixir application. This is possible thanks to the mixed Gleam package that makes compiling Gleam source code from an Elixir easier. Note, recently there was an update to Gleam that lets us compile Elixir files and Elixir libraries within the Gleam project. I tried to wrap Scenic into Elixir, but ran into some errors and didn't have time to explore more, but I'm pretty sure it should be doable. Continuing, the first thing that happens within the Elixir project is that Elixir spawns the Scenic UI components in a supervisor, and the home scene makes use of the chess library to retrieve the state and draw it on the screen. But this current setup only permits one client to control one chess game. In an ideal world, the client will be capable of controlling as many chess games as it's authorized to do. Also, Gleam can do much more than just be a purely functional library. To be able to create multiple sessions per client, I devised a trio of components. The Elixir registry for storing Gleam processes, Elixir's dynamic supervisor, and Gleam's own interpretation of a gen server that stores session information. The dynamic supervisor from Elixir standard library lets us spawn an undefined amount of sessions. When a new session is spawned, we use registry as a routing table. This is helpful because now we can talk to sessions by using a user-defined name. Finally, the session is a Gleam flavor of a gen server, or to be more precise, a Gleam actor. Syntax is a little bit different, but this is what the actor looks like. On the left, we define the shape of our messages. These are used to type the actor's callbacks. And on the right, we can see that the actor's star function is being initialized with the predefined callbacks, covering all possible messages that this actor can take. This system works, but it is currently not stitched together into the Scenic client. But I just wanted to show that Gleam can also be a powerful tool for OTP runtime concerns. And because this is a process, it can work along Erlang and Elixir, as we can see, because it's working along registry and the dynamic supervisor. There's still a lot to do to make this a deck-building chess game, but I'm going to wrap up for now. So I just want to say thank you so much for your attention, and I hope this presentation was useful. And thank you so much to my work peers, Carlo Gilmar and Lorena Mireles, for all the moral support and tips to realize this talk. I would also like to say thanks to the Erlang Solution Americas team, which reviewed my presentation and made it just better. Finally, the Gleam Discord is a great place to be, and I have to say that it is my current happy place on the internet. I spent about 3 months preparing for this talk, so I'm also sending my love to Mayra and Milena, my wife and my daughter, which have supported me through the long nights. With that, I could start taking questions.
Yeah, thanks a lot, Raúl.
Thank you.
Right. So we don't have virtual questions, so we'll be taking in-person questions. Anyone? Sure. All right. Oh, OK.
Did you happen to test any of this? And what did that story look like for you, testing Gleam inside of Elixir or any of that?
Yeah, so Gleam right now wraps up, when you are compiling to Erlang, Gleam wraps up Gleam unit, eUnit as a testing library. So I was able to test within Gleam, but once it compiles to Erlang, everything is wrapped up into eUnit and run as Erlang tests. So it is possible to test, but this is probably a system that will be improved in the future to have our own set of unit test standards.
All right, cool. Any other question, anyone? Yep.
Thanks, congrats on your talk. And this is more a speculative question, but I mean, based on your experience developing Gleam, I believe in your work you either use Elixir or Erlang, right?
Yeah.
And do you think that maybe in the future, Gleam will have almost the same status as Elixir and Erlang for the Bean?
Yeah, that's an interesting question. I will steal a phrase from Louis People, the creator of Gleam, and say that Gleam is becoming dangerously usable for production. There are still a couple of things left to make it production ready. There's some parts of the build tool that might need to be improved. The ecosystem of Gleam also needs to grow. But now that, for example, Gleam can compile Elixir libraries and can compile Elixir files into a Gleam project, it is becoming way easier to just, for example, we don't have like a database library. We can just use Ecto from Gleam, which is pretty nice. So I think, yeah, in the future, it will be perfectly usable, but it all depends on the Gleam community investing in the tools right now.
Right. Okay. Yeah, I guess that was it. Thanks, Raúl. And, well,
Yeah.
thanks, everyone.
Thank you so much, everyone.